Okay, I think that we can start with introduction. It's okay?
Oh, yeah.
Okay, okay, perfect. Okay. Okay, Fabienne Doumolin is associate professor in the Department of Biomedical Engineering of Academic Mehmet Ali Aydınlar University in Istanbul. She studied first biology, graduated in biochemistry, and then completed her PhD with an European label in organic chemistry in Lyon, France in 2002. She was a postdoc in Italy, in Pisa, and afterwards she settled in Turkey in 2005. She is an international recognized expert on the design and synthesis of tetrapyrrolic derivatives, mainly phthalocyanines for photodynamic therapy. She authored so far 5 research articles, 3 book chapters, and supervised a dozen master and PhD students. She has been awarded several Young Scientist Awards, and she is one of the Turkish national nods for the International Day of Light, was elected officer of the Executive Committee of the European Society for Photobiology in 2015 and 2017, and is member of the Royal Society of Chemistry. She regularly organized the Photodynamic Day in Istanbul. Fabienne Doumolin is also an associate editor and editorial board member for LSC Advances and Journal Porphyrin and Phthalocyanines. And she has co-edited the book series Porphyrin Science by Human, published in January 2020. The title of the seminar is
I can say it if you want.
Okay, you can show because I am not email here. Yeah.
Okay.
Okay. Thank you very much.
So I cannot share my screen. Thank you. I cannot share my screen. I think I need to be allowed.
Okay.
I did it. Now you should. Yeah.
Okay. Yeah, it's working. Okay, so if I got this, do you see my full screen?
Yes.
Yeah.
Yes.
Okay.
Yes,
and if
yes.
I change, you see the change of slide?
Yes, sure.
Yes.
Okay. So, well, first of all, thank you for the invitation. Really, it's a pleasure, especially as I missed with COVID the opportunity to visit you last year. So today I'm going to talk about the way that we improve the properties of phthalocyanin for triplet state association. And this work, I mean, I am affiliated to Mehmet Ali Aydınlar University, and currently I am an invited professor in Lyon, École Normale Supérieure de Lyon, until today, actually. So I wanted to acknowledge these two institutions. So this is Turkey. I'm going to go with the pointer. The dramatic earthquake was just there, and I mean, it's really here. It's still far away from Istanbul, as you can see. That will be the European and the Asian part of Istanbul with the Bosphorus. So you can see that we are here in the Asian part of the of Istanbul. This is the picture of the university. So you can see it's a quite new university dedicated to health topics. So if we go into the type of molecules I'm going to speak about today, you know, I'm sure you've heard about these natural porphyrinoids that are macrocycle tetrapyrrolic derivative. There is this chlorophyll D that you can find in vegetables, the heme from hemoglobin, one of the vitamin B12, and all they have in common is that, and they are natural. In the case of phthalocyanin, it's from the same family, but they are artificial compounds. So still tetrapyrrole, you will see if you put together 4 pyrrole, connect them, add nitrogen atoms and benzene ring, and you have the most pristine, simple phthalocyanin structure. And then what we do as chemists is playing with the opportunity we have to modify the structure. We can introduce a metal, and in this case, sometimes we can also introduce actual substituent. We can introduce substituent in this position that we call peripheral, or this one that we call non-peripheral. You can play with the number of substituent, the nature of the substituent, the fact to have the same things or not on each of the 4 subunits. And with this modification, you can control the solubility, the aggregation, the photo properties, sometimes the redox properties, and introduce some chemical functionalization. And this is all the things that have been introduced to phthalocyanins. You can see that the whole periodic table has been attempted. If you want to know more about this compound, there is this chapter that is really getting into the details. So the substitution pattern is important, and there are 2 examples that I can show here. You can see here this has all zinc phthalocyanin with all 8 exyl chain, and the only difference is the way that these exyl chains are attached to the phthalocyanin microcycle. So it can be a thioether ether in peripheral, non-peripheral position, it can be a normal ether in peripheral position, or sulfonyl in peripheral position. And this modification are inducing these different maximum absorption and photo properties, which are also depending on the solvent. In this case, this example where we have a shift of between these 2 phthalocyanin of the maximum absorption of 55 nanometers, it's even what we could call the same substitution pattern, no metal, S-octa alkyl substituent, but the bulkiness of the terbityl here is inducing a distortion of the microcycle. This is disturbing the homolumo gaps, and this is inducing this shift, which is really significant in their maximum absorption. So what do we do? Usually, we focus on the design and chemistry and the synthetic strategy of phthalocyanin, and it can be to have new substitution patterns. Sometimes people are just reclaiming some specific structure, and we modify their properties and functions. So this is just to say where we stand in the chemistry of phthalocyanin. This molecule does not exist, nor this one, because unlike the porphyrin chemists that are really controlling the substitution patterns of porphyrins, it's still not done for phthalocyanin, as said Clifford Lesnoff in the 4th International Conference on Porphyrin and Phthalocyanin in Roma quite a long time ago. So we are trying to get new asymmetric patterns. This is what were known when I arrived in Turkey, and we developed some specific stoichiometry and reactivity strategy. The first ABAC phthalocyanin that you can see here, this was the first structure, and this was with reproducible yield around 12%. May not be a lot for some chemists, but in the chemistry of phthalocyanin and with these degrees of asymmetry, that we can say that it's quite a success. Some phthalocyanin also 2 macrocyclic can complex a lanthanidion, and in this case that's really difficult to selectively functionize only one of the subunits. We are now dealing with 8 subunits. Anyway, we managed to do that with also some some stoichiometry strategy, some reactivity strategy. And I just want to thank again this reviewer. We always complain about reviewer. This one was a nice one. So what do we do with this molecule before entering into all the details of the triplet application? Molecule that I like a lot, as you can understand. These are the different properties that they can have, of course, depending on the structure. And these properties allow us to use them in different applications that can be from carbon dioxide reduction to imaging, battery, etc., etc. So you can see that there is really a wide range of application for this molecule. So we do some for the energy, catalysis, environmental, but mainly for health, in this case with triplet state involved. So just quickly to show you really the potential of this molecule, we have used them as carbon dioxide electrochemical reduction catalysis with a careful design. The cobalt was in order to have redox property. This one to maintain the trimethylammonium was in order to maintain the carbon dioxide molecule close to the cobalt, and the terbityl here to be soluble for the purification and also in order to be adsorbed on carbon nanotubes. And this is one, if not the most robust system that has been described with organic catalyst for this application. On the complete other spectrum of application, this kind of molecules where you have two iron phthalocyanine bridged by a nitrogen atom, they can reduce methane at room temperature. So this is also not trivial. And we needed asymmetric structure to get more into the details of the mechanism of reduction. And thanks to these molecules with an electron-rich and electron-poor microcycle, we could show that the hydroperoxo oxidant is binding preferentially on the iron, electron-rich iron side, which is giving us more insight about the reactivity of this compound. So let's go in the core of our topic with phthalocyanine in photodynamic therapy. We use molecular and nano photosensitizer, phthalocyanine-based photosensitizing system. So just to, I wouldn't know if everybody is familiar with PDT, so this is just a kind of precision. The photosensitizer is only the system that you are using to generate singlet oxygen. A photodynamic process is what you do then when you use this singlet oxygen, and it can be for a wide range of different applications, involving or not health topic. And when then you are killing cell, you are in photodynamic therapy. It can be against cancer, against age-related macular degeneration, antibacterial and antimicrobial. And for each of these applications, we are going to have to make a different design of the photosensitizing system. So these are all the electronic events that are involved in the generation of singlet oxygen right here once the photosensitizer has been irradiated. This is used when the photosensitizer is administered to a patient, when the correct amount of time is waited for the maximum optimal accumulation of the photosensitizer in the tumor, irradiation, no tumor anymore. And the specificity is based on two different things. First of all, you choose where you apply the light. And second of all, the lifetime of singlet oxygen is short. So it has no time to go to another place than the place of irradiation to inflict damage that we wouldn't want. And this is a big advantage compared, for example, to chemotherapy. So when we want to design photosensitizer, this is a little bit what I call the list to Santa Claus of all the properties that we would like in a photosensitizing system. So as chemists, we are working on developing some of them. If you want to know more about the different type of photosensitizer and the molecular and nanoengineering, you can refer to this special issue of PPS that I edited a few years ago, and you will see, you may find it quite interesting, I hope at least. So we said that we excite the photosensitizer with light, and in this case, it's really important to be able to use near infrared wavelengths for two reasons. First of all, the longer are the wavelengths, the deeper they penetrate into biological tissue. And the second reason is that we have what is called this phototherapeutic window. At this wavelengths, I mean, near infrared is starting at 780 nanometers, but let's say that we start at 700 for this phototherapeutic window. These wavelengths do not excite endogenous chromophore, which is a big advantage for us as we don't want. In this case, when you want to use such wavelengths, you can look at this different member of the porphyrin family. Porphyrin have a maximum absorption here. Chlorine are just a little bit here. Bacteriochlorine are really good, but that's a nightmare to synthesize. And you can see that phthalocyanine is here in the ideal wavelengths that we want for this. So this is also a review about the recent use of phthalocyanine for PDT against cancer, if you're interested in the topic. These are the phthalocyanine that have entered a clinical trial or advanced stage of utilization. This is a liposomal formulation. This is in Russia, in China, in the US, and this one has been taken out of sale, as far as I know, but has been used a lot, in particular for labeling. So what do we do in our case? This was the first series of phthalocyanine that was developed in my lab for PDT. This was with the galactose tetraperipheral substitution pattern, glycerol tetraperipheral, glycerol non-peripheral. And you can see that the most efficient is this one. And this has been attributed to the fact that this is the position of the substituent, the non-peripheral one, that is limiting aggregation. And we want to limit aggregation because otherwise we are self-quenching the generation of singlet oxygen. And when this is the absorption is like that, we have aggregation. When it's sharp, we don't have. And this can be related to the better activity of this derivative. We wanted to improve it further, and we replaced one of the glycerol on one of the subunits by a iodine atom for with two purposes in mind. First of all, further improve the amphiphilic balance, hence the cellular internalization, hence the photodynamic effect. And second, benefit from what is called the heavy atom effect, that is promoting the generation of singlet oxygen because it's promoting the generation of the excited triplet state of the photosensitizer. And we get indeed on 3 different cell lines, subcellular, submicromolar IC50, and also absolutely excellent result on antivascular PDT with tests performed on the vascular occlusion experiment of the chicken embryo chorioallantoic membrane. Still with the same basis, we kept this triglycerol and introduced carbohydrate at the end, this time of a spacer, with the purpose and the idea that because some cancer cells are overexpressing some sugar carbohydrate receptor at the surfaces, we will promote also in another way the cellular internalization of the phthalocyanin. And at that time, click chemistry was very popular in the chemistry of carbohydrate, not that much in porphyroid. So we decided to test the effect of a grafting made by click or normal glycosylation. And we could see that the presence of the triazole generated by the click reaction had a negative effect on the monosaccharide, but not on the disaccharide right here, probably due to a small bulkiness effect that is preventing the good recognition of the carbohydrate. Completely different strategy that we developed. In this case, it was in collaboration with Sylvie Duquier from Clermont-Ferrand and friends. She is working on chalcones that are analogs of combritastatin A4 that are promoting the depolymerization of tubulin. When it's the neovasculature of the tumor, then the tumor is starving. And we decided to try to combine this VDA effect, vascular disrupting effect, with the photodynamic effect. The first derivative was made out of this one, where the chalcone was grafted here with the phthalocyanin. Unfortunately, it was not enough to be able to perform at that time. We had no formulation collaboration. We couldn't perform because of a problem of solubility, the biological test, but we decided to design a new compound with this, in this case, only one chalcone on the phthalocyanin and water solubilizing PEG chain. And this was a good idea with a much better phototoxicity with a synergic effect of the conjugate compared to the reference phthalocyanin. We kept we retained also the VDI efficiency of the chalcone, which is a little bit slower than the reference chalcone, but anyway, still present in a good extent. Since we have been making different structure that we hope to be testing soon. Now I would like to very briefly mention antibacterial PDT. I'm sure you are all aware about the problem of antibacterial, antimicrobial resistance. And this is mainly because antibiotics have a very specific mode of action. In the case of photodynamic effect, because this is a large and untargeted oxidative damage that is going to touch and affect everything in the cell, it's very unlikely to have a development of resistance. And this is all the type of application that could be benefiting from photodynamic therapy. In our case, so far, we have only one work reported with this phthalocyanin that was really super efficient in killing Staphylococcus aureus, even a resistant strain. The thing is that we should acknowledge that it's not that difficult to kill gram-positive bacteria with photodynamic effect. Now we want to make something that is going to be also able to kill gram-negative bacteria. We also do a little bit of nano research, and in this case, we need not only to design the photosensitizer itself, I mean the phthalocyanine, but also the full nano object, the nanoparticles. Nanoparticles, indeed, nanomedicine more generally has been really raising a strong enthusiasm in the last decade. This is the reason why the, nanomedicine has been given one of the few European technology platforms of Europe. And the reason of that, the basis of that is that there is what is called the enhanced permeation and retention effect. And this is based on the fact that a tumor is something that is growing very quickly. And because it's growing very quickly, it's developing its own neovasculature in order to get all the supply of nutriment and oxygen that it needs. And because this neovasculature is made very quickly, it's not done very properly and it's deficient. There are holes in it, and therefore a nano object circulating in the bloodstream won't be able to exit the bloodstream in healthy part of the vasculature, but only in the tumor area. So this was really very hopeful, but a couple of years ago, anyway, this review of the analysis of nanoparticle delivery to tumors showed that it was not that efficient. Usually, this APR is working very well on tumors that have been grafted onto rodent, but they are so big compared to the size of the rodent. I would say it's a little bit like a human being with a football balloon of a tumor. That would not happen. So then there have been this buzz around that, of course. Many people have given their opinion about that. And anyway, it's about the fact, what is reminded is that we have, when we have nanoparticles, we have nano platform. And even if we don't have purely the APR effect that we would write, which is itself heterogeneous, like every cancer is, we can benefit from them to make some platforms. So we have been working in different directions. For this one, we wanted to have this equivalent fluorinated. The thing is that when this one, the analogous, is water soluble, this one is not. So we needed some formulation. It has been done with pluronic-based triple copolymer micelles, and we could demonstrate in collaboration with Janusz Dabrowski in Poland that it led to an improved biodistribution and that 20% of the mice treated were still in remission 1 year after treatment. Imagine what is 1 year in the life of a mouse. For human being, that would be really a success. We have been using different type of nanoparticles, polyacrylamide nanoparticles, in collaboration with Rose Boyle and Francesca Giuncini, which is now in Liverpool. The idea was to demonstrate the feasibility of grafting in an orthogonal way different moieties on the polyacrylamide nanoparticles, including an phthalocyanine in water. Different also strategy, this time using sequeoscan nanoparticles made of phthalocyanine. These nanoparticles, usually they are prepared from a trialkoxysilylated organic precursor. There is no silica source. It's something completely organic, and in this case, the organic part represents up to 80% of the structure, which can be also periodic. So that will be the idea. Here you can see such an object going to be grafted with this acid with the 2,3-hydroxysilane. Here would give this object that can then self-condensate into nanoparticles. This is a project that was developed in collaboration with Vefas and in Turkey, and in Montpellier, Magali Garibobo and Jean-Olivier Dio. And in this first work, what was done is that having a porphyrin with tetra-propargyl substitution and the same with phthalocyanine. They could be clicked on the trioxysilane derivative, and nanoparticles could be obtained. The nanoparticles are retaining the photoproperties of their parent molecules. We have a good homogeneity of the structure. That was fine. But the phthalocyanine showed a very good activity for photoacoustic imaging, but compared to the porphyrin here, were very bad in killing cells. So we decided, in order to improve our system, to make the same, the analogous octa substituted this time phthalocyanine. So now we had 8 propargyl moieties right here that could be clicked, form phthalocyan nanoparticles, and that was a good idea, probably because of thanks to a better mesoporosity of the phthalocyanin. You can see of the nanoparticles, as you can see here in this high resolution 10 microphotograph, and we could demonstrate an excellent photo killing with 780 nanometers, 810 nanometers killing, as you can see, with the pulse laser. And also these nanoparticles could be further functionalized and be used to vectorize nucleic acid like cRNA and be transfected in cells, this time as a photochemical internalization. So last but not least, I haven't been following the time, but I'm sure I am close to the 30 minutes. I wouldn't know. Another triplet state application that we are developing, this is nearly over. And in this case, this is in collaboration with Kasper Modpulsen, who was in Sweden at the beginning of the collaboration and is now in Spain, in Barcelona. And the idea was to use the triplet energy of the phthalocyanin, hence with far-red wavelengths, to promote the isomerization of azo moieties, as you can see here. And the problem in this case is that you don't want any singlet oxygen generation. You want a maximum triplet state, but then the de-excitation should promote the isomerization of the azo and not the generation of singlet oxygen. So it could be performed in biosourced plastic, which was quite good work, this one being more at the wavelengths that we would like. So conclusion very quickly, phthalocyanin are wonderful. I hope I managed to convince you. And just a couple of announcements right now. I just would like to, just in case, if you don't know, attract your attention to this series of 4 issues of the Journal of Porphyrin and Phthalocyanin that I've been converted in a 3-volume book series highlighting, promoting the role of women in porphyrin science. I have put together 2 editors' collection in RSC Advanced on photodynamic therapy and phthalocyanin also, in case you are interested. You may know that the next Congress of the European Society of Photobiology is going to be Lyon in France at the end of August, 27 to 31, this summer. There is a nice congress in Montpellier also. I'm just saying that because I am in the organization committee and because it's great. And this big congress compared to an EUPAC congress that is going to be in July in Istanbul. Feel free to be interested and to join. That's really going to be huge here. Several Nobel Prize that are going to be plenary speakers. I want to thank the structure that I funding my research, mainly TÜBİTAK and also the Turkish Academy of Science, Campus France. Obviously, I have many collaboration with France, and Mustafa Parlar team and Araştırma Vakfı. Want to thank my group also, even if it was more than 6 months ago. I need to refresh this picture. We are open to collaboration in question, just in case that you know people applying to a Marie Curie fellowship, individual postdoctoral fellowship in Turkey and in this widening country have extra chance to be awarding a fellowship. So you may be interested, just contact me in this case. I want to acknowledge the collaborators that have been taking part of in all of this work also all over the world. And I would like to thank you for your interest, and I would be happy to answer questions that you may have.
Okay.
Thank you, Fabienne.
Thank you, Fabienne. Thank you very much, Fabienne, for your very nice talk. And now there is time for the questions.
Yes, just feel free, even if it's not mandatory, of course. But
yes.
It's Friday afternoon. People may a little bit, even if phthalocyanin are great every day. We don't know.
Okay, I have a question. So, what is the exact compromise between solubility of zinc of phthalocyanine of phthalocyanine and hydrophobicity of these systems to optimize photodynamical process?
We can introduce, I believe that you know Peter Zimjic and Veronika Novakova. They made very nice phthalocyanin derivatives with bulky substituent that they managed to be completely soluble in water without any aggregation. And we are developing also some substitution patterns that are still promoting the water solubility, but that should lower even more the aggregation. The thing is that it's not that much a problem. I mean, you need to be biocompatible and to